In this video, we'll start to talk about the graphical properties of trigonometric functions. To do this, we'll need a quick review of trig functions, we'll need a quick review of transformations of graphs, and then we'll dig into the periodic properties and the even-odd properties of the trigonometric functions. So let's review the trig functions. Recall that for any t, a real number, let p xy be the terminal point on the unit circle determined by t. We define sine of t to equal y, cosine of t to equal x, tangent of t to equal y over x, provided that x does not equal 0, cosecant of t to equal 1 over y, provided that y does not equal 0, secant of t to equal 1 over x, provided that x does not equal 0, and cotangent of t equals x over y, provided that y does not equal 0. These are the 6 trigonometric functions. And if we're interested in graphing them, we need to know a little bit about amplitude, period, horizontal and vertical shifts. So for y equals a f k times the quantity x minus b plus c, where f is one of the 6 trigonometric functions. This function has amplitude, absolute value of a, horizontal shift b, vertical shift c. When f is sine, cosine, cosecant, and secant, the function has period 2 pi over k, and for tan and cotangent, the function has period pi over k. Now remember what those graphs look like. Top left-hand corner, we've got sine of x, starts at 0, goes up, drops down below, and meets back up with the x-axis for one period, 2 pi. Cosine starts up at 1, drops down below to -1 at pi, and then back up to 1 at 2 pi, also for a period of 2 pi. Cosecant and secant both are the reciprocal functions for sine and cosine respectively. These have a little bit different look to them, but as we've talked about, since cosecant and secant are the reciprocal functions of sine and cosine, they meet at the same point, pi over 2, 1, but then as sine and cosine leave their highest point, cosecant and secant will start to get larger because we have 1 over a decreasing value. Both of these have period 2 pi, and 2 pi. And then tangent and cotangent. Tangent defined as y over x on the unit circle, cotangent as x over y on the unit circle, and both repeat themselves every pi units. Now thinking in terms of our amplitude, period, and horizontal vertical transformations, one thing to notice is that if we shifted sine of x by 2 pi units in either direction, we would get sine of x back out because we would just land on top of itself. Same thing with cosine, cosecant, and secant. If we shift any one of those graphs 2 pi units, we'll just get the function back out. For tangent and cotangent, since those both have period pi, if we move them pi units in either direction, we'll land on top of the graphs. This is what we mean by the periodic properties of the trigonometric functions, is that if we shift them a certain number of units in either direction, we'll end up on top of the original graph. Another thing to notice is that for sine and cosine, as well as cosecant and secant, and tangent and cotangent, there's a way to manipulate the graph to get to the other one. For example, to get from sine of x to cosine of x, we can write y equals sine x, and then how much do we need to shift to get to cosine x? Well, if we're thinking about sine of x, we should see that we're pretty darn close already if we just move sine of x over to the left pi over 2 units. This is just cosine x. And then you could define something similarly for cosine x, cosecant x, secant x. For tangent and cotangent, to get from tangent to cotangent, we have to not only flip it over the x-axis, but we also have to shift it over a little bit. So at the very least, we need to do negative tan, and then x. Since tangent's centered at the origin, we can move it either direction. Let's just say we move it to the right, pi over 2, and that gives us cotangent. So these are some of the interesting kind of periodic properties of the trigonometric functions. Summarized, sine of t plus 2 pi, or minus 2 pi, equals sine of t. Cosine of t plus 2 pi equals cosine of t. Tangent of t plus pi equals tangent of t. Cosecant t plus 2 pi equals cosecant t. Secant t plus 2 pi equals secant t. And cotangent of t plus pi equals cotangent of t. Now I didn't write all of the properties out where we shift a function, but like we said, if we take sine and we move it pi over 2 to the left, we'll get cosine. And if we take cosine and move it pi over 2 to the right, we'll get sine. Now to talk about even and odd functions, we should recall what that means. By definition, an even function satisfies the property that f of negative x equals f of x. And by definition, an odd function satisfies the property f of negative x equals negative f of x. Even functions happen to be symmetrical about the y-axis. And you can kind of see this by looking at the definition of an even function. For some negative x value and some positive x value, the function takes on the same y value. You know, a classic example is thinking about f of x equals x squared. If we plug in f of negative x, we get negative x quantity squared, which that equals x squared, and that equals f of x. So that's how you would prove that it's even versus odd. If we happen to get negative x squared, then it would be odd, but that wouldn't happen. So for our trigonometric functions, we should think about which ones are symmetrical about the y-axis. So looking back at our graphs, I think it's easy to see which ones are symmetrical about the y-axis. Cosine and secant. Sine, cosecant, tangent, and cotangent are all not symmetrical about the y-axis. So let's do a little bit of algebra just to confirm that our suspicion is true. Let's say that g of x equals cosine of x. If we give g negative pi over 4, that is, we give cosine negative pi over 4, we just get root 2 over 2 out, right? And what's the other quadrant where we get a positive root 2 over 2 out of cosine? The first quadrant, when t equals pi over 4. So we can say that cosine pi over 4. So this equals g of pi over 4. So see, we started with g of negative pi over 4 and ended with g of pi over 4, thus proving that cosine is even. How about h of x equals cosecant of x? So let's try h of negative pi over 6. So this is cosecant of negative pi over 6. And that should give us 1 over negative 1/2. Which if we factor out the negative, that's negative 1 over 1/2. We know that this is 2, but I'm not simplifying it just to keep track of what's what. And then 1/2 is the y-coordinate of the terminal point determined by pi over 6. So this is negative cosecant pi over 6, thus showing that cosecant is odd. To consolidate all of this into a nice chart, I have revised a previous chart that I had in another video. So I have all the functions in the leftmost column, the domain, the ranges, and then even or odd property. So sine, cosine, tangent, and cotangent are all odd, and cosine and secant